So I'm going to talk about safety, and we'll see where it heads. And this is the group of people that I'm working with. I've been interested in automated vehicles for a much longer time, about 30 years. And then that interest disappeared, and then it's got revived again. And this is a quick summary of what I'm going to discuss. First, why intersections and why not freeways? Second, there are two approaches to enhance intersection safety. One I call the city planning approach, which goes under the name Vision Zero. And then the second, the more technocratic approach, which is automated vehicles that are going to solve all our problems. I'll focus then on automated vehicles. I'll go through sort of an anatomy of a particular accident and see why it's going to be difficult to have safety. And principally in intersections, so I'll discuss how to construct intelligence in the intersection. And then a work to be done, or future work, which is how to make intersections in a city safe. So why intersections? For the usual reasons that intersections are dangerous. Lots of accidents and fatalities occur at intersections, even though they occupy a small amount of area. Some numbers over there. Red light running is another big cause of fatalities. So there's 165,000 accidents a year due to red light running. And the last bullet there is about automated vehicles. So automated vehicles which are being tested in California, if they get into an accident, they have to report to the Department of Motor Vehicles how and what happened. And 88% of their accidents occurred in intersections. So why intersections are difficult is because they have complex geometry. The operational rules are difficult. You can see some of the timing diagrams or the traffic diagrams in an intersection. The signage is complicated, right? So if you're doing automatic recognition, that makes it difficult. And so as I said, there are two policy prescriptions. One is Vision Zero, stemming from the planning community, and then automated vehicles. Let me first focus on Vision Zero. What is that all about? So Vision Zero is, I think, as a phrase, it started in Scandinavia, but then it's got imported into the US. So many, many cities like these in California already have Vision Zero plans. And basically they want to eliminate fatalities and serious accidents through infrastructure modifications. And what are those modifications? The first one is what they call road diet. Road diet means you eliminate a lane. So instead of having 3 lanes, you'll have 2. Instead of having 2, you'll have 1 lane. And enforcement of speed reduction. So for instead of 40, you go to 30, to 15, and so on. Second one is a sidewalk extension. I don't know whether you have them here, but we have them in Berkeley a lot. Sort of extending the sidewalk so that the distance that a pedestrian has to walk between sidewalks is reduced. So that's this, they call it bulb out. And the third is protected bicycle lanes, right? More and more bicycles, and to buffer the cyclists from moving cars. But doing all of these then funnels traffic into the intersection, so that intersection becomes a focus or locus of accidents. And now they're proposing more expensive modifications of intersections going under the name protected intersection. We have one of them in Berkeley. Vision Zero is maybe half a dozen years old. And there's some data coming out of that. And the data suggests that it leads to fewer crashes and fewer fatalities, but nothing dramatic. So in New York City, for instance, there are 12 slow zone streets. They've given the diet treatment. And at the end of 4 years, they have the same crash rate, but the casualties have dropped, right, by 4%. Speed enforcement is the main driving force. Why is that? So these are Vision Zero techniques. So the top diagram tells you that if you get hit by a car at 40 miles per hour, chances of survival is 15%. And the survival increases dramatically as you reduce the speed, right? So at 20 miles per hour, the probability of death is 5%. So one way to reduce fatalities is just to reduce and enforce speed reduction, right? So that's that. But we can see the pedestrian deaths have climbing. Over the last several years, pedestrian deaths in the country have been climbing, and they are going up. On the right there are some of the reason, I mean, how modifications you can do. So you can have these poles out, mid-block crossings, shorten the crosswalk, refuge islands for the pedestrians, traffic cameras, police, and speed limits. So these are some of the modifications that people do. I'll give you an example about throughput lots of bulb outs. So this is a picture right in front of Corey Hall in Berkeley. So this is the way the street used to be. So this is Corey Hall. So it had 2 lanes. Then they extended this sidewalk and that sidewalk, so it bulb out. So 1 lane disappeared, right? So that is, and the cross lanes is sort of reduced by maybe 6 feet, right? But the result is that the right lane is gone, and so through traffic and light turn traffic merge into the same single lane, and that creates problems. I mean, you have bottlenecks created. There's a vehicle which wants to turn right, but there are pedestrians crossing, so the vehicle is stuck, so everybody behind is also stuck, right? So there's significant throughput loss. Is there a safety gain for pedestrians? It's not so clear because the pedestrians come into the way of bicycles, and so that part is not so clear. But anyway, that is the idea. So in Berkeley is full of these bulb outs now. This is the protected intersection. There's one of these in Berkeley, of course. And so there's a big bulb out, and then there's a gap here. So there's a safety setback crossing. So these people can now cross over here. There are these refuge islands. So people can move over here and then wait here to cross again. That's one thing. The other thing is to have a friendly signal phasing, so a special phasing for bicycles and not just for cars. Again, max throughput is reduced by maybe up to 50%. The cost of these intersections is between 250,000 and 1 million plus, so it's expensive. It's inflexible, right? Because you cannot rechange the concrete if the traffic pattern changes. And so the Berkeley's protected signal, it doesn't have a bicycle signal. So that's another thing that happens is some people go halfway because bicycle signal now will require a lot more wiring and a lot more cost. So we forget about that, but we do the rest of the things. So that's all I'm going to say about Vision Zero, except to note that it is inflexible, right? And doesn't recognize, there's no concession other to intelligence, right? It's simply more concrete and restrict the movement, primarily restrict the movement of right turns, so that vehicles have to slow down to 15 miles an hour or 10 miles an hour because the right turn is now much sharper in order to make the right turn. And the second thing is to reduce the amount of space that the pedestrian needs in order to cross the street. If the street is not very big, it's okay, but if the street is big, like in Phoenix, Arizona, then that's not even feasible because the amount you can reduce is not much. So automated vehicles come to the rescue. So this is an announcement from Waymo, this is an announcement for GM, and they all quote this figure that 94% of the accidents are caused by human error, and they're going to eliminate all of those, so we'll have very few accidents as a result. This is now the most recent entrant, which is Intel. Intel bought this company called Mobileye, and they're going to create an automated vehicle, and they promise a verifiable, certifiable, 1,000 times safety improvement over manually driven cars. Just as a caution, the 94% error, which everybody quotes, is misleading, right? If you go back to the original report, based on 2005, 2007 data, it says explicitly that in none of these cases, was the assignment intended to blame the driver for causing the accident. Right? The accidents are assigned to one of 3 causes: environment, vehicle, or human driving. I mean, there's no other cause. Right? And so they explain how, in particular scenarios, it is a much more complicated chain of events which leads to an accident. So it's a little bit arbitrary that you assign it to a human driver. You don't assign it to the environment if it's clear, right? If it's not foggy and not raining and not slippery, so that goes out. And the second thing is vehicles. Well, vehicles are very rarely do they result in faults, such as a flat tire, all of a sudden a tire bursts. So automatically, almost the way the procedure goes is that everything is assigned to human driving. Now there's a backstop. So supposing you feed, so what is the backstop in automated vehicles? So I'm going to give you some example. Drive.ai is a recent startup which is doing AI for driving. And so they say our AVs have less than 100 millisecond reaction time, and so I'll come to that question mark. But that's a short. Human reaction times vary between 100 milliseconds and 1 point something seconds. Then what they do is so they will have, as a backstop, if your automated vehicle fails, then there's a telechoice operator monitoring multiple vehicles sitting somewhere, like those drone operators. Just they're monitoring these vehicles and will take over control in case the control fails. If you believe that, you can believe a lot of other things. There's a Phantom Auto is another startup which is providing that kind of service. An operator sits in front of multiple cameras and tries to drive or steer the vehicles. Now, this is one example. So Department of Motor Vehicles requires a new requirement that if your autonomous car you want to test is not going to have a driver. Currently, most vehicles have a test driver to properly respond to emergency vehicles. So then GM Cruise, which operates in San Francisco, they requested the city to provide them, as I said, 1 to 2 officers and a fire truck and a fire engine and an ambulance to drive around so that the GM can learn about how these things, emergency vehicles, operate. And they will decide where they should drive, and the city said no. So this is the kind of thing you have to get into. Skeptics. So there are quite a few, not that many, but quite a few skeptics. So this is a skeptic who is an R&D person from Nissan, and he said that he describes the scenario, that there's a cone of vehicles which is shunting traffic to the left, crossing over a double yellow line, right? And a worker holding a sign. And he said there's so much cognition you need here that he's very, very dubious whether automated sensing systems can recognize them. So in his view, it's not going to happen for the next 5 to 10 years. The double yellow line is important because most automated vehicles are trained to follow the traffic rules. Crossing a double yellow line is violating a traffic rule, right? So that becomes a dilemma for automated vehicles. So you have to have exceptions that if there's cones, you follow the cones, and so on. This is another one. This is he's a CEO of a company called Easy Mile, which does automated van service in campus environments. That's his thing. So he says door-to-door service without a safety driver is not likely to happen for decades. And he says functional safety is impossible to enforce in complex environments. And he thinks only a few use cases can be addressed in 3 to 5 years. Most important is the last sentence, is that you must get rid of the safety driver, otherwise there's no business. Right? The business is only going to come from, not too many private individuals are going to buy this thing, but in any commercial use, if it requires a driver, safety driver, in addition to all the electronics that you're going, that's not. So that's important. This is a quote from a piece. So Waymo is the most leading. They do a lot of testing in where are they? In LA, I'm not LA, in the Bay Area, Monterey, not Monterey, Mountain View. So they do a lot of, so people are familiar with these vans that Waymo runs. So she says, she nearly hit a Waymo minivan because it stopped abruptly while making a right turn at the intersection. And she screamed, "Go," she shouted angrily. After getting stuck in the intersection, midway through her left turn, she's stuck behind this car. And then other people, the reporter said, the company's safety drivers regularly have to take control of the wheel to avoid a collision or potential safety situation. Waymo vans might stop for at least 3 seconds at a stop sign. That's another nuisance. So most of the automated vehicle accidents in intersections tend to be rear end because the automated vehicles stop frequently suddenly, and the people behind don't realize that they're driving behind such a vehicle, so they run into each other. A last point about from the Financial Times reported, they queried all these automated vehicles about how they train their safety drivers, and they said that the biggest AV companies, including Waymo, spend less time training their backup operators than Uber, whose safety record is terrible. So typically they train safety drivers for 2 weeks or 3 weeks to run these vehicles. What is the safety record after all of that? So, again, if you have an accident, you have to report to the DMV, and also you report how many miles of automated driving you've done. Right? So you divide number 1 by number 2, and you see that the automated vehicle rate is 40,000 miles of autonomous driving between accidents. You compare that to the US, human driving rate, It's 500,000 miles per accident reported to the police. So not trivial accidents, but whenever you have some damage, you report to the police, and in between accidents is 500,000 miles. So you compare the two, human driving versus. Now, this is per accident, but there's something else which the automated vehicle companies report, which is what they call disengagement, self-reported disengagement. And this is the definition that the DMV gives of a disengagement. Disengagement occurs when a failure of the autonomous vehicle is detected. The safety driver detects some failure, or the system also automatically detects a failure, or if the safe operator of the vehicle requires that the test driver take over. This is the test driver's decision that this thing is not safe, so I'm going to take over. So how frequently does disengagement occur? That happens every 5,500 miles. Right? So if you think about a disengagement as a near, quasi, pseudo, dangerous situation, then that happens much more frequently than human driving. So it's not very good. Here's when you do a disengagement, you have to report what the disengagement is. So these are one sheet from Waymo between April and May of 2017 about their disengagements. And these are failure detections. So how long does it take to detect a failure and the safety driver hits the brakes? 0.9 to 1.3. For humans, the median is 0.9 seconds and 25% take 1.2 seconds. So the reaction time, even it is not 100 milliseconds that Andrew Ng reported for Drive.ai, it's actually much more, right? 10 times more than, well, that's a big reaction time, right? 1 second, you may go, depending on your speed, you may go anywhere between 20 and 40 meters in that 1 second. And so automation is not necessarily immediate, which is the implication that you normally get, that it'll be so much faster than humans. Yes, it is true, because, I mean, there's a tail of human reaction time which goes into several seconds if you're very old or if you're drunk, or something like that. So it is not that, right? Whereas but there's a big tail even for automated vehicles, if you look. How do they work? Well, these are the three things, right? Sense. Finally, your battery gave out. So this one. Yeah. So three things: sense, plan, and control. So sensing is what you'd say is sensing. You sense by sensors, and the sensors universally are lidars, right, which rotate or have a beam that rotates. Radars, and cameras. So in a big Waymo car, you'll have so many of these sensors. So those are continuously operating, and use it to detect objects in the field of view, classify them. Is it a vehicle? Is it a pedestrian? Is it a fire hydrant? Is it a whatever? You estimate the position and speed of these vehicles, and then you predict the trajectory of so-called dynamic objects. So you may see 500 objects around you. You don't try and predict all of them. I mean, there's too much compute power, right? So you first decide which of these objects are likely to be dynamic, that is to say, likely to move. So cars that are parked, you ignore, right? So then you predict those, right? We'll see. So and then you plan the path to avoid the trajectories of the ones that you predicted. And then you calculate, this is now the standard control problem, you calculate the actuation for the steering, braking, and acceleration. So this is roughly what it looks like. So these are the other objects. So this is your vehicle. And then these are the objects around you. So this may be a bus. I've forgotten what the icons stand for. This might be a bus. There's a bicycle, etc. And these are the trajectories that you believe these objects will take. And then your job is to avoid them for the next 3-5 seconds, and everything is recalculated. Okay? So that's I cannot resist not quoting Musk for sensing. So he says, once you solve cameras for vision, autonomy is solved. Right? So although I don't know whether the new Teslas have a radar or not, but they used to have radar and cameras, but nothing else. They don't have lidars. So, and if you don't solve the vision, nothing is solved. But that's sort of characteristic overstatement. What are the US statistics? 100 million vehicle miles per fatality and 1.2 million miles per serious injury or per injury. Automated vehicles are very far from this kind of behavior, right? So the 94% is, you decide how much percent improvement you're going to make each year. I want to go to Mobileye because they guarantee. So let's see how their guarantees amount to. Right, so they call it responsibility sensitive safety, which is incorporated in Intel's design as adheres to safety assurance and scalable to millions of cars. So it's a formal model of safety. And I'll just give you one example of the formal model. So suppose two vehicles on a single lane. Then they calculate something called the minimum safe distance. And what is it? So is this number. So V sub r is the speed of the vehicle, the rear vehicle. Rho is the reaction time. V sub f is the speed of the front vehicle. There's a maximum braking acceleration you get and the minimum braking acceleration, etc. So it's got this number. So I plug in some numbers, right? So first example, I assume both vehicles are stopped. So they just parked one behind the other at the stop sign. So the vehicle speeds are 0. If I assume rho equal to 2, which is 2 seconds, that's a bit much, okay? And you put in those numbers, you get that the minimum distance is 93 meters. So if you're standing, if you're parking, one car parked, stopped, the other car has to be 300 feet away. That's the safe distance according to this. If you say rho equal to 1 second, which is reasonable, then you divide this number by 4. So that's 25 meters, 75 feet. Then I haven't seen anybody who is parked behind the stop bar who is 75 feet between vehicles. If I make 10 meters per second, which is 22 miles per hour, this number goes up to 140 meters. Nobody ever drives this way, right? So this may be fail-safe driving, but nobody can drive like that, right? So that's the Mobileye story. I'm going to focus on one crash, all right, for drawing some lessons. So this is an Uber crash. And in Tempe, Arizona, on this particular date, March 24th of last year. This is the diagram you get from the police report. So there's two vehicles that are relevant for us, vehicle 1 and vehicle 2. Vehicle 1 is somebody driving a Honda CR-V and coming from here and making a left turn. So she happens to be a woman, so it's a permissive left, right? So she doesn't have a left arrow, so but it's a green. So the other one is vehicle 2, which is the Uber driving on the rightmost lane and going through. So that's the setting. The Uber is going at 38 miles per hour through the intersection. It's a 40 mile per hour zone, so 38 is permitted. Whether it's wise or not is a different story. The Uber is driving straight. There are two other lanes, but these two other lanes, there are vehicles who are stopped there because they're stopped on the other side, so it is so they cannot drive, right? It's what's called spillback in traffic terms. So there's a spillback of traffic, but miraculously not on this lane. So the Uber comes, and when it comes there, the light turns yellow. But the driver finally says that the Uber is programmed to go through yellow as if it's green, right? So it goes through at 38 miles per hour. It doesn't matter. I mean, at 38 miles per hour, you're not going to be able to stop in 2 feet anyway, so that's irrelevant. This lady says that she didn't see anybody. These two lanes were stopped, so that was a problem. She also saw in the countdown timer of this crosswalk that she had 5 or 7 seconds left. And she didn't see any vehicle here. So she went. The result was a crash, because this is going at 38 miles per hour, and the crash led to this crash. That's the police diagram. The Uber then hit this pole on the intersection, flipped on its side, and hit 2 other vehicles. And those are the 2 vehicles that you see. So that was that crash. This is a simulation of the crash, just so you can imagine what it's going to look like. So this is the crash from the left turning vehicle. So it stopped, makes a left turn, didn't see any vehicles, and then this is the one on the, so this one will maybe illustrate better the top. Oops. See, this Uber is coming fast. She's coming, stops, makes a left. This one cannot see that. Right. So what are the lessons from this? So I think there are so many lessons. First, Uber did not predict that the light would turn yellow when it entered the intersection. Couldn't. I mean, we don't predict when the light is going to change. Did not know that the traffic in the opposing direction could make a left turn. Right? There was a permissive left. Doesn't have to be. It depends on the signal pattern. The safety operator saw the Honda, he says, too late, as the traffic in the first two lanes created a blind spot. So those two cars are parked, so couldn't see that. The Honda driver says, I was about to cross the third lane and then saw a car flying through the intersection but couldn't brake sufficiently fast to avoid that. So how could that crash have been prevented? Well, there's several things that could have happened. The intersection could have provided a phase prediction that the phase is going to change in the next 4 seconds, 3 seconds, 2 seconds, etc. So you have some advance warning, slow down, right? You could have even programmed your vehicle to slow down in that case. It could have said that the phase permits the vehicles to turn left. So then you could be warned that such warning could occur. Blind spot information that it could have told the Uber, the intersection, if it detects this left turning vehicle, it could have said to the Uber that there is a blind spot you have and there is a vehicle turning and occupying that blind spot. Similarly, it could have given that information to the driver. Right? So that if any of these things had occurred, or all of these things had occurred, and they would have been taken into account by the two drivers, or the automated vehicle and the driver, then that accident could have been prevented. So there's spatial uncertainty because you don't know who has what the phase looks like to the other approaches. There's temporal uncertainty because you don't know when the phase will change. So if those two are provided, then you can do that. Lastly, no matter how many sensors you put on the vehicle, you will not get this information. Right? You don't know when the light will change, and you don't know if there's somebody in your blind spot. So that's what the intelligent intersection will provide, right? It's missing it. Here's some other examples of common intersection accidents. There's a signal confusion. So this vehicle wants to turn right. It sees this other vehicle on the left turn lane, but doesn't know, it only sees a red. Doesn't know whether this vehicle has the right of way or not. If you don't know the full phase, you don't know what that vehicle can do. Here's another situation. This vehicle wants to turn right. There's a pedestrian, but doesn't know whether the pedestrian is going this way or that way. It takes a couple of seconds to figure out which direction. This is a common occurrence, which is a rear accident. So this vehicle is behind right. The other one, this vehicle sees a yellow and may decide to stop or may decide to go. The one in the back expects it to keep going, like those Waymo vehicles, and it doesn't, so there's a rear end. These are similar other accidents. This is a red light violation. So this vehicle has entered the intersection 7 seconds into the red. Fortunately, this vehicle sees it and slows down and swerves, so avoids that particular accident. This is the yellow interval dilemma, right? So there's a crash. There's a pedestrian coming and doesn't see it because that's a common situation. In Berkeley especially, you have to be very, very careful because pedestrians usually are looking at their iPhones when they cross the pedestrian, right? And okay. So the functions of the intelligent intersection is to remove the spatial and temporal uncertainty. How do you do that? You tell the vehicle of the complete signal phase. That is not just in your approach, but all the other 3 approaches, assuming a 4-approach situation. And you predict the time of the next phase change, right? That's called signal phase and timing information. So you provide a signal, or a message, which gives you the signal phase everywhere, and the timing, which is when is the expected. Tell the vehicles of conflict zones. I'll explain what conflict zone is, and a potential blind zone. So this is static information. This is just the information about the map of the intersection. It tells you these are the likely places where you could run into an accident. That's the conflict zone. And these are the likely places where you may have a blind spot, and so you need to be careful. If you just do that, there's too many of these. So you want to give some real-time information, which is say these blind zones are occupied, right? So that requires some sensing. Lastly, you should warn vehicles of a red light violator. As I said in that particular example, that violator was 7 seconds into the red, so he would have been seen 2-3 seconds in advance before he enters the intersection. And you could have taken some action. You could warn, as I said, warn the vehicle. Alternatively, you could have extended, depending on the time when it occurred, you could have extended the green light for that violator, so the violator could go through, and put red on the other ones, right? So that's, now there's a moral hazard here, obviously, because you encourage that behavior. So you have to combine that with a stiff fine, right, to overcome the moral hazard. So that's a possibility. Let me explain a little bit about signal phase and time, about signal phase, how timing change. So this is a particular intersection in Montgomery County. It's got 8 phases. So for people who don't know transportation, traffic lights, so there's phase P4 and P8 are these phases. This is sort of the minor direction for this. So when that's the green, this is the timing diagram. So phase P4 and P8 will last on this much. So this is one cycle up to here. Then P1 and P5 come on, and then the blue phase. So P4 and P8 are this cross direction. P1 and P5 are the left turns, P5 and P1. And then P2 and P6 are the major through fares. Okay? Now, this is an actuated signal. That means that the phase duration is not fixed. It will depend upon the sense traffic. And so here's 6,000 cycles. And so if we take one particular cycle, then the green phase, which is the P4, P8, this can extend. There's a minimum amount of 32 or something, which is for pedestrian crossing. And then extra amount depending upon whether people are push buttons or whatever. So that's the green. Then comes the red phase, which is the turns, right? Which sometimes is not there if there's nobody making a left turn, and sometimes it's quite a bit. And the remaining time in the cycle is given to the through phase. Okay? So that's what it is. So now let's look at this particular picture, which is trying to predict at any time t how much of D4 is left. D4 is the blue is this. Right? So you're standing over here. You're waiting for that phase to terminate, and you don't know how long it'll take. And so it's a statistical thing, right? Because it's a random variable. So at any time t, you've already so many seconds into the cycle, we know that you have minimum 32. So for that you get here. And then after that, the amount of waiting time normally would go down. But not necessarily, because normally then all of a sudden it got actuated, so it may increase. So this is the conditional expectation of the remaining duration. Right? So you could broadcast this, and that's the idea. You broadcast this every 100 milliseconds. So your vehicle, if it's automated or not automated, doesn't matter, tells you how much to expect that you're going to be stuck there. Right? This is a lot used for eco-driving. So you are wanting to go through this intersection, and you're waiting for the green light. So it'll tell you when the green light is likely to start, right? And so this is the information that is used to control your vehicle profile and your engine so that you'll reduce the amount of fuel you consume. I go to blind zones and conflict zones. Okay. So just to give you an idea, so these are all the possible movements you have, right? There's a through movement, there's a right turn movement, and a left turn movement. So let's look at a right turn movement. So there's a trajectory. Somebody that a vehicle would follow if it were making a right turn. Lots of trajectories making a right turn. So you group them all together, and I call that a guideway. All right, so the guideway is a bundle of trajectories making the same turn. So that's the blue one, which is making the right turn. There are many other guideways, right? So here's the guideway of pedestrians crossing the street. Here's the guideway of a left turn from the north. Here's the guideway from west to east. So there are lots of guideways. Wherever two guideways intersect, that means these are two movements which can coincide. That's a conflict zone. Okay? So that's all this thing is about. Right? So now let's look at this particular movement. This one is making a right turn. That's the white trajectory. And the magenta thing is the guideway for that right turn movement. How many conflicts does this vehicle have with that right turn? There are 7 conflicting movements. What are they? The white ones, left turn from the north, a through movement from the west. These are conflicts with vehicle trajectories. The black one, left turn, through, and a right turn. These are 3 bicycle movements with which you may have a conflict. Finally, you have 2 yellow ones, which are the 2 pedestrian. Right? So there are 7 conflicts. So while you're negotiating this right turn, you have to somehow or the other take care of these 7 conflicts. What do you have? You know the phase that you're in. That's one information. Second, you can see some things. That's the second information. So that's all the information you currently have. Now let's see what happens. Right? Let's first go to the phase information. So you see a red. This is your vehicle, the ego vehicle. That's you. You are making a right turn. And this is what you see, a red turn. You don't know what are the lights the other 3 directions are seeing. There are 4 possible configurations of a light phase. This is number 1, which is yours, but you don't know it. You could be 2, 3, or 4. In 2, you only need to worry about coming from the left. In this one, you only need to worry about the traffic from the front, and in this one, you only need to worry about traffic from the right. If you knew that, there's a lot of simplification can occur, right? So let's see what happens. So several conflicts you can resolve visually. So you're making this thing, and you can see these 2 trying to make a left turn, but you can see them. So you know if they are making a left turn or you're not making a left turn. So I assume that if you can see them, I don't worry about it, right? Similarly, this pedestrian, you can see, it's visible from you, so we don't worry about it. So those 3 conflicts are gone. But next to you is this parked vehicle. So there's a cone of thing that is obstruction. So you cannot see this vehicle, you cannot see that vehicle, you cannot see this, also this pedestrian you cannot see. So there's still conflicts remaining because there are agents in your blind zone. So the only way you should go is if you can decide that these 3 objects are not present, which is not what we do, right? And we sort of go anyway and hope for the best. Also, we may be more alert than normal if you're making this particular right turn, and you may make sure that you're crawling, and as you crawl, you see more and more, right? So that's another. But if you're an Uber vehicle, you may not be programmed to do all that. So let's look at the Uber crash situation, right? What is happening? So I'm assuming that this vehicle has taken care of all the other possible conflicts, right? So the only conflicts can come is making a left turn. The only conflicts can come from the 3 lanes of through vehicles, plus there's the pedestrian crossing, right? So there are 4 possible conflict zones in this left turn path, 1, 2, 3, 4. We don't worry about C1 and C2 because she can tell that these guys are not moving, so there's nobody going to show up there. This one, she thinks there's nobody there because she doesn't see anybody there, but there is a conflict, right? So we want to see what is the blind zone for her. Similarly, if this vehicle is moving this way and these two are blocked, so there is a blind zone. Right? So what is the blind zone calculation? So this is a blind zone calculation. So this is the blind zone from this vehicle's viewpoint. So situate yourself at this point, and then you can have a certain angle of view, right? So that angle of view I've drawn as this vision zone, right? So these are the vision zone you have. So you can see everything in this vision zone unless it's blocked. And this part is blocked by these vehicles. So this whole thing is a blind zone, right? So this vehicle should not move unless she is sure that there's nobody in this blind zone. You calculate the amount of blind zone. This is the upstream traffic given a certain speed, how far you need to be able to see, or how far. Okay. Symmetrically, from the viewpoint of the Uber, if it's sitting over here, it can see that these two are blind zones. So everything here is in the blind zone. So any left-turning vehicle in here, this Uber cannot see. Right? So it needs to be warned that there is somebody there, or trust. So if you had these warnings, then how would that picture look? So this is a left-turning car. It does the same thing as before. Stops. This is the Uber. It gets a conflict. Then it's called clear. Then it gets a yellow light. Then it gets a red light. Stop. Right? So the result. So if this automated intersection was there, intelligent intersection, it would have avoided that particular crash. The red light violation. So this is a Waymo vehicle which was going through an intersection in San Jose. This truck violated the red light. 7 seconds into the red light, it entered and crashed with this vehicle. This is the picture that I had shown before, and this is, we had put a camera at an intersection and recorded this thing. So this vehicle has a green and this vehicle has red. But this one is going to violate the red light. So this is the car with the right of way. This is the red light violator. It has 7 seconds before it comes here. Right? Fortunately, in this case, it could see, and so it stopped and swerved, and so avoided the red light. But this vehicle, the driver said he saw it, but it's too late. Right? So that's what happened over there. So that could readily be prevented. How? Because currently, in this particular intersection, there was no red light violation camera. But the way those red light violation cameras work is somewhere upstream. It measures the speed of the approaching vehicle. It knows what the phase is and decides that this vehicle is not going to stop before the light turns red, right? And takes pictures and issues a ticket. So it's got about a couple of seconds before it can do that. So that's enough time to somehow or the other provide a warning or extend the green light or do something, right? So all those things could be prevented. Now, okay, given that, I want to know how should I construct a citywide intersection safety report. So this is now all work in progress, okay? So I will take all the intersections in LA and say this intersection is more dangerous than that intersection, and this intersection will profit more if you provide some investment. That investment for intelligent intersection would be between $10,000 and $30,000 in my estimate, depending on how big it is, right? So how many sensors you need, how many possible blind zones there might be. So the steps are intersection geometry, so I need to calculate the geometry. Then map the guideways, conflict zones, and blind zones. That's a basic notion. Collect the crash data and traffic data to figure out how to rate that intersection. And calculate the crash probabilities. So San Francisco, so we have OpenStreetMap. So for all the San Francisco intersections, we have this data. And there's about 20 attributes, which I won't describe for you. Longitude, latitude, diameter, et cetera, et cetera. And these are the intersections. So that's one thing you can get from OpenStreetMaps. It's not automatic. I mean, you have to, there are bugs in there, so you have to fix those bugs, but it's not, it's doable. So here's an idea. Then how do you construct the intersection catalog? So this is an OpenStreetMap data you get for a particular intersection in San Jose, right, in First Street and Component Drive. So you start with that, right? So you can identify, or there's metadata available for each of these things. So it's basically, basic construct is dots, right, points on with the coordinates, right, latitude, longitude, and it gives you dots are connected, are grouped together into what they call ways, W-A-Y. So that's like, so this is a way, right? That's a way, and so on, and that's a way. So that's the basic information, and it'll also give you the number of lanes. It'll give you the mid points on the center of the lanes. So that's your basic information, right? So that's the kind of stuff you get. Then, so that particular intersection, this is the Google Earth view of that intersection, right? So now you take that data and you construct the guideways. So the guideways we construct by taking that this is your entry lane into the intersection, and that's the exit lane from the intersection. Now you connect all that. Okay, so those are the guideways, center lines of guideways. Right? So either they go from the center of the lane or center of the crosswalk. So now this guideway also there's a rail. So there's a rail guideway, and it has bicycle lanes. Those are the green. So we have all those. So the greens are the guideways for bicycle lanes, so the centers for guideways. The blue are the vehicles. The red are the crosswalk. So that's the first thing. The next thing now is to make a guideway. So the idea is for a lane movement, it'll be lane wide. Right? So that's what you get. So those are some of the guideways. Now this one is, so we're computing a blind zone for a particular, so we're looking at this particular left turn, and we're computing its blind zones. First of all, let me show the conflict zones. So the conflict zones are where two of these guideways intersect. Right? So here's a conflict zone between this train and this left turning vehicle. Conflict zones with the pedestrian crossing and that vehicle. Conflict zone between two lanes of through traffic, etc. Right? So those are the conflict zones. Then we look at a particular conflict zone and see what is the blind zone corresponding to that. So in this particular case, it is this conflict zone together with this right turn. And you see that all of this could be a potential blind zone. Whether it is actually a blind zone or not, I mean, whether it is occupied or not will depend upon whether there's vehicles. So you can compute the blind zones and the conflict zones for every intersection and reasonably automate it, right? So in the case of San Francisco, there's about 1,500 signalized intersections, so there'll be 1,500 such stories. This is the story for Berkeley. So these are the intersections, and these are some categories of complexity of an intersection. So it's got more than 4 legs, 0% tertiary, various categories which you get. These annotations you get, or metadata you get from OpenStreetMaps, what kind of street it is. So now we have the intersections. We also have for San Francisco all the crash that took place for the previous 5 years. So this is the crash data, gives you the intersection, and so forth. Right? Description of the intersection involves a pedestrian, not involve a pedestrian, just property damage or actual injuries, and so on. So you get all of this. This is California public data. This is an idea of what you do. This is for San Diego. So you have here the kind of crash which took place, head-on crash, following too closely, etc. And these are various signalized intersections. And you can see a correlation between kind of crash and a kind of intersection. So that's what we want to do for San Francisco. The last thing we want to do is to calculate a crash probability. So this is just the elementary exercise, right? So this is a vehicle, this is the same intersection as the Uber crash, except this time this vehicle wants to make a right turn instead of going through. And I want to know what is the probability of a right turn and hitting a pedestrian. Well, it's straightforward. So the crash will happen, we hypothesize. You want to make a right turn, and you are blocked from seeing this pedestrian because these two vehicles are sitting there. So I can calculate the probability that there's a queue, and within a particular cycle, what is the probability that there's a vehicle going to make a right turn? And the last thing I need, the probability there's an intersection, that somebody's crossing the intersection. So that I can get if I know the sort of crosswalk data, and I know the right turn data, etc. So if I do that, then in a peak hour, this probability is very, very high, right? So probability of making a right turn on a red is almost 1. The probability that a view is blocked is going to be 1 because it's peak hours, so traffic is going to be stopped. Not all the traffic will be cleared during the green. And there's a high probability that somebody's walking. But in fact, you don't have that many accidents, these calculations suggest. So there's something else which is going on, which is that the pedestrians are very alert. So they don't just decide that I'm going to cross the crosswalk and go blind, right? So this number needs to be understood better. When is it that a pedestrian will run into a car? So, but anyway, we can make rough estimates of all the other kinds of crashes which are possible and assign probabilities to them to come and assess an intersection safety probability. So I'm going to conclude by saying that Vision Zero infrastructure modifications, A, are expensive, B, are inflexible, but C, they do provide benefits, principally by reducing speed. That's the main thing. But the inflexibility and the penalty for mobility is significant. Automated vehicles and others, pedestrians, cyclists, drivers, they don't know the intersection phase fully. They cannot predict when the phase will change. They don't know where the blind zones are. They don't know if the blind zones are occupied. And that spatial and temporal uncertainty can be a contributor for crime. There are, of course, many other causes. You're drunk, so it doesn't matter. Giving you any information doesn't help, right? Or you're distracted. So those are the only other major causes. And an intelligent intersection can remove this uncertainty, right, by providing these pat messages. And then you could rank safety of every intersection. And if a city has a plan to improve its safety performance and has a limited budget, then this thing can tell you how to rank the intersections and proceed.